Hey, what's up guys? Welcome to another video. I have a very special nickname for this Project Ugly Sandwich. Why do you ask? Well, let's see why. This is a portable LED panel with 32 LEDs. What can it do? Vlogging in the dark? Check. Using it as accent lighting to light up scenes and fill in shadows? Check. Light for macro photos? A huge check. Clicking long exposure photos? Check. As a general purpose nightlight? Check. It also has a standard 1/4 inch tripod mount. After making the relatively bigger LED panel in the last DIY video, I wanted a portable battery powered one which you can mount it on top of your camera or use it to light up the background or to use it as a fill light. Coming to the LED panel, I had 100 of these SMD white LEDs and decided to make my own LED panel using them. Started off by testing out a single LED with my variable bench power supply. These LEDs were their brightest at around 3.6 volts. Any further increase in voltage saw very small change in brightness for a huge increase in current draw. I decided to have the maximum voltage to be capped at around 3.4 volts instead of 3.6 to reduce the heat output and also improve battery life. It was time to make the LED panel itself. Here I used these prototype boards with connected rows. This saved a huge amount of time. Imagine connecting all the LEDs in parallel on one of these. I soldered all the LEDs with the terminals in two parallel rows. It took some time and practice to solder these SMD LEDs without melting them. In the end, it all worked out. Also painted the front facade of the panel with white paint to make it look less like a PCB. I connected the finished panel to the power supply and cranked up the voltage. Would ya look at that? With all the 32 of the LEDs, the panel got really bright. I quickly measured the current draw by the panel at various voltages, and at about 3.4 volts it pulled about 900 milliamps. That puts every LED at around 28 milliamps. Even at this voltage, the panel got a little warm after a few minutes. Hence, I decided to make a rough heatsink for it to improve the cooling. It is important to keep the LEDs cool because of their behavior, which I'll get to in a moment. I cut a small metal piece from scraps and attached it to the back of the panel using a lot of thermal goop and some double-sided tape. Attached this panel to a bigger cardboard such that there is some air gap between the metal plate and the cardboard for heat dissipation. This is already on its way to become a sandwich. Time to design the power supply for the small yet bright LED panel. Before doing that, a little theory about LEDs. Trust me, you would want to know this. LEDs are nothing but diodes which emit light, hence the name. Like all normal diodes, these also have a minimum forward bias voltage which happens to be around 3.3 volts for the white LEDs. Here's the thing, once you cross this bias voltage, for every small increase in voltage, there is a huge increase in current, a typical diode behavior. Another characteristic of LEDs is that their forward bias voltage decreases with increase in temperature, meaning as the LEDs warm up, the forward bias voltage reduces ever so slightly. This means more current draw at the same voltage. More current means more heat, and more heat means more current, and this vicious loop just goes on. So how to solve this? Ideal solution is to build a constant current power supply. That's the best method to drive the LEDs. But I am still going to be building a constant voltage source with a voltage which is lower than the maximum brightness. Thankfully, the change in bias voltage is also very small in this case and does not affect the current draw significantly. Now let's build the power supply. I chose lithium-ion batteries because they pack in a lot of energy in a small package and are rechargeable. This is a tiny DC to DC buck converter and it can provide up to 3 amps at the output. After checking out the datasheet of the buck converter IC, I found out that the minimum voltage required for the input is around 4.75 volts. So a single lithium cell wasn't gonna do, which peaks out at 4.2 volts at maximum charge, and they go up to or less than 3 volts at 0% charge. Two of them in series then. I proceeded to grab a couple of old phone batteries. One of them is 1000 milliamps and the other one is 1250 milliamps. But remember that it is always best to use identical cells to make batteries. I soldered both of them to a TP4056 charger and protection boards, soldered the inputs in parallel so that I can charge them both from a single USB port, went ahead and connected the outputs in series. Wait, do not do this. It took me a while to realize that the grounds of the input and outputs of the charger boards are not isolated and are basically the same. So connecting the inputs in parallel and outputs in series results in shorting off one of the cells. Luckily, they didn't catch on fire. To solve this problem, I added the push button which needs to be released before charging and pressed before using. A very rough solution, but does the job. This gives us a battery pack which goes from about 8.4 volts at 100% capacity and to about 6 volts at 0% capacity. Once that was done, I hacked the potentiometer on the buck converter. Boy, this took a long time because I am an idiot and didn't look at the recommended circuit in the datasheet from the beginning. After going through a lot of resistor values and potentiometers, finally found a perfect combination. With this combination, the voltage went from about 2.4 volts to 3.4 volts. Even though the lithium-ion battery voltage varies more than 2 volts when it discharges from 100 to 0, the output voltage is regulated to the value you set, so constant voltage across the board. Now I made a simple comparator circuit to indicate a low battery and also soldered it to the PCB. I also attached all the power boards to the PCB using double-side tape and attached the PCB to the batteries. Yes, the ugly sandwich is almost complete. Made a small cardboard for the back panel with the cutout for the charge switch. Mounted the potentiometer knob, which in turn also held the cardboard in place. Attached the front LED panel with Velcro so that I can potentially switch the LED panel for a different one which focuses the light, unlike this one which spreads out the light evenly. Once that was done, I attached the whole thing to a small wooden block using hot glue. I had prepared the wooden block earlier by drilling a hole and screwing in the tripod mount. There are some things which can be improved greatly with the power supply and of course the enclosure. That's for the V2 of the portable LED panel. Speaking of battery life, I get around 1.5 hours at full brightness and about 6 hours or more at around 50% brightness. That's pretty decent for such a setup and size. That's about it, guys. Thank you for watching. Please do leave some constructive comments which will help me improve and make better videos. See you in the next one.